weakly nearly R0 spaces. This presentation is based on the paper written by T.M. Nour and Ahmed D.J. Nour, and a vast majority of definitions and theorems is taken directly from this article, so you should look at the bibliography at the end of this video. Well, assume that we have a topological space X tau. And recall that by the very definition of topology, tau is closed under at least finite intersections and arbitrary unions. This is clear. And moreover, it contains empty set and X. Now we shall use the notion of regular open set, that is such A that interior of its closure, as we can see here, is equal with A itself. And its complement is called regular closed set. Clearly, if A is regular closed, then the closure of its interior is equal with A. Each regular open set is also open in the context of tau, and each regular closed set is closed. Moreover, the family of all regular open sets can be considered as a base, or basis if you prefer this term, for certain topology tau star. And tau star is contained in tau, so this is because, as we said, each regular open set is also open. A space X tau is called semi-regular if tau star is equal with tau. And then we have so-called delta open sets introduced perhaps by a guy named Velitsky. We say that A is delta open if for each of its elements, so for each X in A, there exists, we may find, a regular open set U such that X is in this U, and of course U is contained in A. And clearly the complement of delta open A is called delta closed. And going forward, we can speak about the closure of A in X tau star, that is about the smallest regular closed set in which A is contained. And we may prove that A is delta closed if A is equal to its delta closure. So delta open if for each element there's a regular open set U such that X is in U and U is contained in A. And now we have our separation axioms, which will be discussed later. We say that X tau is R0 if for each open U, if X is in U, then the closure of singleton of X is contained in U. This has been introduced by Shannon. It's nearly R0 if for each delta open set O, here it was open in terms of tau, here it's delta open. If X is in O, then delta closure of its singleton is contained in O. This was introduced by Jane. Weakly R0 if an intersection of closures of all singletons, yes, intersection with respect to all x's in our universe X, is empty. This is Mayo. And then we have the definition introduced by Nour and A, that our space is weakly nearly R0 if the intersection of all delta closures of singletons is empty. R0, nearly R0, weakly R0, weakly nearly R0. Clearly, each nearly R0 space is weakly nearly R0. However, one may prove that a converse is not true. Our authors show the following counterexample, which is here. Our space for elements are topology, and one can prove that this space is weakly nearly R0, but not nearly R0. you may consider and calculate this set here, AC. Or you may look to the original paper of Nour and A. Moreover, it's clear that x tau is weakly nearly R0 if x tau star is weakly R0. X tau star. And then every weakly nearly R0 space is weakly R0. Compare these two theorems. Here we said that each nearly R0 space is weakly nearly. And here we say that each weakly nearly R0 is weakly. And the converse of the last theorem is not true. There are spaces which are weakly R0 but not weakly nearly R0. And authors use the following counterexample, which is here. And you may check that the intersection of the closures of all the singletons in the space is empty. But if we replace closures by delta closures, as it's here, then we obtain this singleton of D. And we remember that weakly nearly R0, that this was the definition of weakly nearly R0, and this was the definition of weakly R0. Now we have the notion of delta kernel. Delta kernel of X is an intersection of all those delta open sets such that X belongs to such a set. So a kind of minimal delta open neighborhood of X. Perhaps I'm right. And one can prove that X is weakly nearly R0 if delta kernel of singleton of X is different than the whole universe for any X in the whole universe. And you may find the short proof in the paper, which is in the paper in question by Nour and A. Another characterization, we say that a function between two topological spaces x and y is pre-delta closed if the image of every delta closed set in X is delta closed in Y. And assume now that there exists such map between X and Y. And now we say that if X is weakly nearly R0, then so is Y. And finally, if a space is weakly nearly R0, then for any Y, the product of these two spaces, X and Y, is weakly nearly R0. If a space X is weakly nearly R0, then the product X and Y, where Y is arbitrary, is weakly nearly R0. As for the axioms R0 and slightly stronger R1 in generalized Chasser's topological spaces, namely structures which are characterized only by the fact that they are closed under arbitrary unions, not necessarily under finite intersections, and we do not assume that the whole universe is open. So as for the axioms R0 and R1 in such spaces, there is a paper by Roy, published in 2010 in Acta Mathematica Hungarica, which deals with these topics. However, we do not know if it describes weakly and or nearly R0 axioms in this context. Well, it's behind a paywall. Moreover, we should discuss, or we can discuss, all these axioms in the framework of infratopologies, of minimal structures, and finally, generalized weak structures. As we remember, generalized weak structures introduced by Avila and other authors are the most radical generalization of the notion of topology because they are just an arbitrary families of subsets. So thank you very much for your attention. Oh, there's empty here, and here we have the bibliography, and this is our basic paper.